Welcome to the Control Engineering webcast, IIoT Cloud to Edge. I'm your moderator, Mark Hosky, and I'm happy to join you today on behalf of Control Engineering and CFE Media and Technology. CFE Media has met the standards and requirements of the Registered Continuing Education Program. Credit earned on completion of this program will be reported to RCEP at rcep.net. A certificate of completion will be issued to each participant. As such, it does not include content that may be deemed or construed to be approved or endorsed by RCEP. Industrial Internet of Things, IIoT, architectures incorporate elements of edge, close to the process, and cloud, on or off-premise, application and analytical capabilities, and this webcast answers important related questions. The learning objectives for the course are to outline factors that help determine what mix of cloud-based applications and edge-based computing and communication investments and architectures to use. Examine how cloud and edge technologies fit with existing automation, controls, and other operational architectures already in place. Learn how cloud and edge technologies integrate with and bring greater value to existing automation systems and devices. Determine how to design and consider safety and cybersecurity as integral and ongoing part of IIoT cloud-to-edge architecture. To get the best results from the webcast platform, please make note of the following as you participate in today's event. If you're having technical problems, click on the question mark at the top right-hand corner of your screen to bring up a list of system checks to make before escalating to an online technician. If you're experiencing issues with your slides or audio, please refresh your browser or click the Refresh Media button directly under the presenter's headshot. You can control the volume setting of the webcast by adjusting the volume on your computer or by adjusting the volume on the webcast platform. If you need a technician, type a message into the Ask a Question box and someone will get to you as quickly as possible. Answers to your technical questions will be answered in the Answered Questions box on the left side of your screen. You can use the Ask a Questions box to type questions for the speaker during the presentation for the Q&A session at the end. You can ask questions at any time during the presentation, and we'll get to as many as time allows. Question for today's presenter will be answered verbally during the Q&A session at the end of the webcast. To download the presentation slides, use the Event Resources area on the left side of your screen. To take the Learning Unit Exam, use the Learning Unit Exam tab option at the top of the screen, and the exam will open in a new browser window. You can complete the exam after the webcast. However, the link will break when the webcast signs off. The exam will be posted with the on-demand version of the webcast. The exam is for 1 RCEP ACEC Certified Professional Development Hour. The webcast is being recorded, including the Q&A session. We'll post the archive on the Control Engineering website in a few days, and we'll send you an email with a link to the archive once it's ready. The method of delivery and category. The event is a live educational webcast presented on January 19th, 2021. The educational category is Technical, Health, and Safety. We'll now pause here for a word from our sponsor. Please stay tuned for the speaker introduction, presentation, and question and answer session afterward. After the video, there may be a short pause to compensate for varying internet access speeds.
If you don't know your numbers, you don't know your business. I learned this the hard way with my first company, so I created NetSuite, the world's #1 cloud business system. NetSuite gives you the visibility and control you need to make smart decisions and grow with confidence. That's why companies who use NetSuite grow 3 times faster than the S&P 500.
Schedule your free product tour right now at netsuite.com/grow.
We welcome to the webcast Jeffrey Shannon, Director, Intelligent Operations for Wood, a system integrator. Jeffrey Shannon is a director in Wood's Intelligent Operations Group. His main focal area revolves around process plants and digital innovation initiatives. He is responsible for spearheading the expansion into new and existing markets, the development and implementation of strategic planning, and overall growth for the business. Jeffrey's role includes, but isn't limited to, expanding operations, technology advancements, technical solution support for customers, and the development of long-term substantial relationships. Jeff, please go ahead.
Okay. Good afternoon. Okay. So what is cloud and edge? The cloud is server systems and software that is hosted by others over the internet. Edge from a cloud perspective is basically anything outside of the cloud. In this presentation, we will discuss the technology and application in the manufacturing environment. I'll first review a few examples of why we want to use the cloud, and also terms that are needed to be understood. Okay. So a few good reasons for using the cloud and edge. So inputs and outputs, or I/O, in proprietary control systems are typically higher cost with use of traditional wiring methods. Administrative work to build and maintain layers of tags to transport the data in the traditional Purdue model is costly and problematic. OT systems have scalability problems. OT knowledge tends to be tribal and indigenous to the operation. Cloud can pay for what is used versus large upfront investment. Cloud provides an open environment for tools where OT is highly constrained due to the high availability needs or concerns of the operation. Okay. So terms that need to be understood. So of course, IT is information technology, or from the Purdue model, it's the basically enterprise business network area. OT, or operational technology, or from the Purdue model perspective, it's process control network. Okay. Cloud, servers and applications that run over the internet and hosted by others, or locally in some architectures, depending on your situation. On-premise, the operating company hosts everything themselves. So edge from a cloud perspective is any device or thing outside of the cloud. Edge from an OT perspective traditionally would be the control processor and I/O, or level one in the Purdue model, at least from the perspective of this conversation. A container, similar to virtual machines. Containers allow you to package software with dependencies, providing isolated environments for running services. Firewall, a network security device that monitors incoming and outgoing network traffic and decides whether to allow or block specific traffic based on a defined set of security rules. A data diode is a network appliance that allows data to travel in only one direction. And sensors, I'll be discussing that from a instrumentation or device to measure perspective. Okay. So single versus multi-tenant, and this is to help get a good understanding of software architecture. Understanding software and its architecture is a highly important area, more so than hardware when we're talking about cloud platforms. Single-tenant architecture serves one customer, where multi-tenant serves many, and is often hosted by others. Think of the comparison between a homeowner with a house, which will be a single tenant, versus a condominium, which would be multi-tenant, where you have many owners involved. The house is completely independent from others and it does not share anything with the neighbors, including maintenance. Condo owners, though they have some privacy and security, basically share common utilities and back-end maintenance. All the tenants benefit from the maintenance, though there is individual upkeep of specific areas inside your condo. If your company has their own hosted cloud, you're basically the landlord in the condo comparison. Hybrid software design, depending on how it was architected and developed, can support both scenarios, but likely not in true cloud-native form. Let's review the table below. Okay. So from a shared resource perspective, the single tenant, the instance or instances of the software are solely to the customer and not shared. In the multi-tenant environment, highly shared between customers with security for isolation. Hybrid, it really depends on how the software was architected and basically developed. So for software as a service, in the single tenant scenario, typically you would not see this, but there are hosted scenarios with internet connectivity that can provide a software as a service-like environment. Multi-tenant, this would be the normal delivery for this type of design, and it's really its prime purpose. In the hybrid scenario, again, it completely depends on the design of the software. So the requirement for internet in a single tenant scenario, if the software architecture requires resources from the cloud or other external network, then yes, you would need internet connectivity. Typically, this design does not require internet access. For multi-tenant, yes, as this design is intended to run in the cloud or edge extension of, you would require internet connectivity in this case. Again, hybrid does depend on the software design, but this is an architecture that might be used to get the best of both worlds in this application. Okay. From a scalability scenario, the single tenant design is largely not scalable, where performance is often dependent on the physical machine it's installed on. A single tenant design is likely to be installed in a virtual machine on the cloud, perhaps, if it's going to be cloud hosted. For multi-tenant, it's highly scalable and designed to serve many. The hybrid approach for modern architecture allows this to be highly scalable, but there is some dependency on how well the software was designed in this case. Okay. Hosting, so multi-tenant is designed to host many, that is the premise. Single and hybrid are also capable of being hosted, where hybrid, if the design is well done, could serve as a multi-tenant-like solution. Okay. From a maintenance perspective, the single tenant scenario, each instance will require independent maintenance and typically is the most expensive upkeep. For multi-tenant, this is the least expensive upkeep, where all users receive the benefit simultaneously, but all users receive the downtime depending on how the provider does their work. So there is some architectures that you can support, live back-end upgrades and downtime where you're not impacting users. In the hybrid scenario, it can really go either way depending on the software design and the use case of the customer. Making decisions. For the remainder of the session, we'll review basically defining the application for who needs it, the expected business value, objectives. We'll cover sensors and instruments, appliances and processors in the IoT environment, various forms of systems architecture, operating systems and runtime, and then have some discussion on basically technology selection. Okay. Who needs it? And really discussing from the use case perspective. Understanding the stakeholders and who needs the value of the application is a critical step to providing the solution. Each manufacturing environment has groups of people who have systems that may be needed to be included in the solution and desires for who and how results are provided. In a petrochemical facility, for example, if operations requires the results of the solution to be presented or interacted with by the operation, basically operators, this may dramatically shift the design requirements of the application to be heavily on the OT side of the fence, limiting the ability to have internet access, where a solution required by reliability could be found to be 100% basically IT and cloud environment. Okay. Expected business value. So this is not a technical problem for cloud and edge, but it is highly important aspect to any change in the manufacturing environment. Understanding the value to the business with good messaging increases the ability for the project to succeed. Alignment with stakeholders gets the help and support needed for the solution design to accomplish the goals. So things that you may want to be able to convey, at least at a high level, are, is it going to be increased profit? Is it cost avoidance, reliability, for example? Is it a compliance issue where maybe it's regulatory? Or if it's a safety concern, that definitely is a very high value to any operation. Okay. Objectives. The needs of the application and assessed risk is going to drive the solution with hardware, software functionality, software architecture, etc. Understanding the existing site systems, networks, security measures, vulnerabilities, human behaviors, and others will define constraints and boundaries to the solution. Okay. So what are the needs of the application? Is it for data acquisition only? So maybe it's connected directly to the cloud, or you have an IoT device that's doing some ingestion, and then you have a cloud ingestion path. Do you need computational functions to be deployed at the edge? Connectivity, connect directly to the cloud, or OT with cloud ingestion path. And then, of course, if it's for control, OT with cloud ingestion path is largely where I lean on that area. So does the application need to be real-time? Semi-real-time. Semi-real-time, for example, is historical data is what I would consider semi-real-time as an example. Or is it periodic needs that could be driven by basically an event? Are there third parties involved? For example, if you have an operations or maintenance contractor that also needs the data, that could be an external company to work with. What are the security concerns for the data? Is my data highly coveted and is proprietary to my company where you need to look at it in a different way? What are the risks to the operation? Are there any systems accessible that can impact operations by an unwanted security event? Okay. The sensors and instruments. The vibe in the sensor discussion has been that this is cheap and easy regarding IIoT. We still need to follow good engineering practice in this area for instrumentation that are installed in our facilities as we perform for the plant today. Nothing has really changed here. So, here's the things that would typically be considered in any kind of a sensor or instrument specification. Of course, electrical area classification, the materials of construction, especially interfacing with a process, meteorological data. What's the required accuracy of the instrument? What's the expected reliability of the instrument by the plant, who is likely to receive the instrument for maintaining? Is it going to be wired or wireless? What are the approved vendors and manufacturers in the facility where you're staying within those guidelines of the plant? The requirements, processes, procedures, installation, has really not changed in this area. Maintenance organizations will be impacted by increased equipment and need to have input to what is being bought. Okay. Appliances or processors. We should basically follow the same criteria as selecting an instrument discussed on the previous slide. There's no difference from specifying a PLC for that environment we're installing. So if we're going to choose an appliance to basically be installed in the field in a plant, we really still have the same criteria to work through. Please note the need for an appliance or edge device with the cloud will be driven by the application requirements. Overall latency will need to be reviewed, for example, in this, similar to how we would review for a typical control system application. An edge device, whether cloud edge or OT edge, in the OT environment, will not be as scalable as the cloud. These, of course, will have fixed processing and memory, and I/O, where we need to size the system right for the application. Using devices with integrated security and that use standards-based methods for applications will make choices easier and provide equipment that typical plant employees can service. Selecting equipment that the plant can maintain is a good choice. This makes handover easier and reduces cost of delivery. So, for example, if we put equipment the plant has not seen, there are training requirements that typically happen, but if we stay within their guidelines, we can have a much more capital efficient project. Okay. Systems architecture, we'll discuss the traditional Purdue model. Much of the industry follows the Purdue model in some form in OT. I'll discuss two different views of the architecture. I've seen many variations in implementation over the years where it is important to understand what's in place, security measures, and how well the system is kept up. So typical designs applied in terms of security, there's typically at least one firewall. Sometimes they're back-to-back firewalls between basically level 3 and level 4 from the OT to the IT interface. Access control and intrusion protection are traditional methods of security. MAC ID filtering plus unused ports typically are shut down. This limits accessibility to only the devices you're expected to have on the network. IP address segregation. So, for example, level 3 in the Purdue model cannot access level 1. Also, that provides routing capability to protect from broadcast storms, for example, so one segment doesn't interfere with the other. So also virus protection. OT often can have a 2 to 6 month delay in virus protection updates due to real-time system certification. So for example, the original equipment manufacturer has to test the virus updates so that the real-time system that's controlling the plant is not inadvertently impacted by the update. There's typically a DMZ with limited access to OT. Often the historian is a common path for routing through the DMZ. The business LAN has aggregate historical data that's not shown on the diagram. So at the business network or enterprise level, where basically historical data is hosted for use. Often there are separate maintenance networks to consider. So for example, a analyzer maintenance network, electrical network, a machinery monitoring network perhaps. There are other options there as well that plants do have. Okay. So continuing on the alternate version that's being discussed for the modified Purdue model. So similar strategies to the previous slide, except often I have limited IP address range segmentation in comparison. Often is an OT telecom network, perhaps, with many network technologies integrated. An example would be a pipeline, or let's say upstream production, for example, that has many dispersed well systems and other field components that are over radio or other telecom type networks also. These are often SCADA-based systems. They do have a similar architecture. And then, of course, the historian on the business land is not shown in the diagram, similar to the other. So the systems architecture for cloud connectivity. Monitoring applications that are not needed to operate the facility are good applications to connect directly to the cloud. This can be accomplished with Cloud Edge, with I/O, or by using a device or appliance to perform the acquisition aspects. The appliance would connect to the Cloud Edge using standard protocols such as OPC UA or MQTT. There are many protocols that can be used. Please be aware that pending the cloud platform, there may be specific protocols you would need for direct ingestion or another protocol stack to move the data. In this diagram, I'm showing a firewall with a data diode. If this application is intended for data ingestion only, it's wise to ensure it stays that way. Plants tend to use installed equipment with capacity available to perform other duties, and at times can have unintended consequences. Please note that the security appliances can cause loss of convenience, where the device may not be able to be configured from the cloud, for example. Utilizing the capabilities of the existing architecture to provide data to the cloud that was intended is a good design. Lower risk and easy to approve. Typically, the enterprise network already has cloud connectivity where data can be transported without adding a new path with additional security risk. Okay. Cloud connectivity continued. A base edge design, including infrastructure with risk assessment and approved for use, is a good way to go. This includes having a consistent software architecture with packaged installation, where each project does not have to go through the software integration effort. Cloud environments often provide some prepackaged software and some development and software development kits. An IIoT and/or edge device, of course, might contain you're going to have an operating system. You do have choices of Linux or Microsoft Windows, for example. You could have, let's say, execution runtimes, such as IEC 61131 environment plus compiler, and any development needed for hardware integration. There's also protocol stacks. So, for example, you have OPC UA, MQTT, Modbus. There are a very large variety of protocol stack choices in the marketplace and that are needed. And then, of course, there's containers or microservices with orchestration, those are basically supporting applications, and you're able to run those microservices on the edge device with what they are packaged and needed without impacting the entire edge environment. Visualization and notifications are high-value functions to support an operation. This alone can significantly improve manufacturing by providing on-demand data and notifying when there's trouble ahead. The Cloud Plus Edge support bidirectional data. For example, we could execute real-time optimization applications in the cloud, but from a security and latency perspective, is it appropriate in your case? There will be occasional network losses, and is one of the reasons why we buffer data on the edge device to prevent that loss of data. Okay. Continuing with system architecture, Cloud Plus Edge. Okay. And again, Edge is an extension of the cloud. Edge is limited by the physical capacity of the device. Edge local storage is needed to buffer against network losses. You may use an OT device for connectivity that connects to the edge device via standard protocols. So for data, managing data, data taxonomy, data integration and contextualization is an enabler to provide speed to value for people who need to use it and data scientists, for example. If you can run the application in the cloud, it is highly likely it can be executed at the edge. The simplified architecture diagram illustrates major areas of software architecture. So if I explain the diagram, to the left under the OT column, that's basically the operations technology systems in place. And the example IoT edge device that's basically doing data collection and has other processing capability. In between, you have your network connectivity. This is also where you have your security appliances, such as Firewall and data Diode, for example, to further protect that network. Under the IT edge from a cloud perspective column, this is where you have that within the edge device, the basically connectivity, protocol, ingestion, and the functions to basically move data, to temporarily store data, for example, so some form of short-term storage, and also application environment where you can deploy applications in the edge that are built, such as artificial intelligence, machine learning, other cognitive services, as well as physics-based models, for example. Of course, in between, you'll still have other security measures between that for firewalls on both sides. Then you have your ingestion into the cloud, which is typically, I noted a communications hub that's also referred to as an IoT hub. The IoT hub basically is brokering the data for where it needs to go, for example, to long-term storage, or some direct ingestion for time series data, where you have more semi-real-time or real-time-like applications that are being performed. Then, of course, you have basically non-real-time analysis work, and that is really more so using the long-term storage path of the data that you have. That's typically where a data scientist would often pull the data for this type of work. And then there's really unlimited applications that you could build, but this is part of the basis for building a real-time digital twin, for example. Also integrating other software that you may use in your platform of data, where an API, where an application gateway has use, or API gateway, and where you have your other, the same and more basically application functions like artificial intelligence, machine learning, and all those applications are basically openly available in the cloud environment to use. Whether that's from the cloud provider, or it's from other third parties who have software in that cloud's store, or applications of your own, for example, that can be run. Then typically you have your visualization, dashboarding, other types of functionality that are, say, more visual to be used, and then also monitoring the cloud performance, your application performance in other areas. But true visualization tools, you can have alarm and event functionality, notifications to users as well, or anyone who needs the information, mobile applications, reporting, and other types of aspects, really fairly unlimited to what's available to you. If you can run the application in the cloud, it can be executed on the edge. So again, okay, for a working example, I'll discuss a wellhead controller in upstream production that may have, for example, a gas lift application. This is an example where control is being executed in the edge device. Please note that this industry has different reliability concerns than a refinery that may only have an outage every 5 years. In this case, the wellhead system has a PLC that directly controls and ingests measured data. The edge device interfaces with the PLC via OPC UA. Flow metering and other unique functions use their traditional devices due to high-speed requirements and latency concerns. These devices interface with the PLC. The cloud edge device provides data ingestion to the cloud with a short-term history for buffering, gas lift optimization model, virtual flow metering, and provides set points to the PLC to optimize the gas lift to recover oil more efficiently. Okay. Operating systems and runtime. So there's some design considerations that need to be held. You cannot freely mix Linux and Microsoft Windows environments, for example, where this needs to be planned with interface methods, but basically your software architecture is a planning exercise to make sure that you have the right design. High availability requirements will impact the technology you select and likely would execute Linux in that environment. Software components selected for Edge may also limit selection options. So for example, if the software component only operates on Microsoft Windows, for example, that is a consideration that will have to be in place for your design. Containers are prevalent in Edge deployment, where the Edge device supports integration using containers, but that also allows you to only completely package for the application everything that that application needs to be successful. For real-time environments, in IEC 61131 or IEC 61499 runtime, may dictate the OS that will be in the Edge environment, for example. Okay. Technology enablers for selection processes. So we'll discuss needs of the application. The architecture of the application should drive the technology selection. Software architecture, in addition to physical and logical, needs to be an important aspect of this exercise. Minimum design documents to drive selection. So a good user requirement specification that definitely aligns with stakeholders. Functional specification, again, that's heavily stakeholder alignment. Physical architecture. Logical architecture, which is more of a communication path. And data flow diagrams are important in the exercise. It also allows you to do a more full risk assessment of what your security concerns are based on the data that's flowing. Other beneficial design documents, such as data hierarchy, data schemas, conceptualization, relationship mapper, and other methods are fairly important for the software, so it's easy for the user to use. And of course, less training as well. End user approved vendors and manufacturers list. Again, those are important aspects. Some companies take quite a long time to actually approve another manufacturer, so it's in your best interest to make sure that you've done due diligence here. Wireless infrastructure is an important enabler for speed to value and capital efficiency. So especially for monitoring systems, it's much less expensive than basically pulling cable. So that really is the bottom line on that. This should help make technology selection easier to evaluate and choose what fits the needs of the application and ultimately the business. Okay. So I'm going to cover a use case using basically a gear pump application. Okay. The symptom in the gear pump was shear pin failure. This event periodically happens when operations is pushing production too hard over design limits of process equipment. The result of the behavior was reduced production for short periods until operations could switch to the backup pump and return to the normal operation. And then, of course, the maintenance cost of servicing the disabled pump. Some measured data was available from the process historian, such as suction pressure, lube oil temperature, feed rate, and motor speed. Motor and pump bearing temperature measurements basically were added using IIoT. Advanced data visualization methods and machine learning were really used to help understand the problem. Time series and event data integrated with visualization methods to help to understand the lead up to the failures. A work order is often treated as an event with the adjusted timestamp to the actual pump failure timestamp in this case. The finding that high bearing temperature of the pump and low motor bearing temperature were consistently indicated before the shear pin failed. Production rate and amps indicate reactor entrainment issues carrying over unexpected materials to the pump. These findings allowed us to predict future failure possibilities, providing approximately 20 to 40 day advance warning to reliability and operations to avoid the event or to decide to accept it and schedule maintenance. The use of machine learning methods such as probability waveforms can be used to monitor for the future events where we are continuously adding value to the operation. Okay. The goal of the application is to provide notification of potential failure of this piece of equipment that is costing the operation. We targeted machine learning as a mechanism in analytics to solve this problem. We had identified that we needed process data, alarm and event data, work orders, and additional measurements in this case due to the machine had little direct measurement. It is much more cost efficient to apply IIoT for this additional measurement data as the install cost is lower than plant's traditional methods. We narrowed the data sources to the process historian that contain process, alarm, and event data, then the work order system, and IIoT edge device and OT, plus cloud edge ingestion of the data. The application had a few needs for storage. The first is time series storage at the cloud edge device to buffer so that we do not lose information on network losses. The second is long-term storage of all the data received for the analytical work that needed to be performed and future tuning of the application. The last need is time series storage to continuously support the need for future predictions based on the results the application machine learning provides. So basically continuous monitoring, watching the new data feed come through and seeing if we can find the probability basically match the waveform. Reviewing the diagram, you can see the path of IT infrastructure moving historian and work order data through their normal enterprise path of the cloud. Data shows going through the communications hub, also called IoT hub in cases, but technically can transport data directly to storage. IIoT has a parallel path for direct cloud ingestion. This simple case study would not necessarily need much work performed in data exploration work for taxonomy, contextualization, etc., to make sense of the information in a meaningful way, since the data set is small. However, moving this to full scale across many assets and plants will need this function in more automated form so that data scientists are not spending all their time trying to find the data associated with the asset. So we've had some studies that have showed that data scientists can spend basically 75% of their time trying to sort the data out. We want people to work on added value components as much as possible. The first step in data science work is to visualize the data to glean what might be learned by simply viewing the information. The other use of visualization is to monitor the application for new events and where you could be seeing a false positive. The rest is notifying using selective means such as email, for example, and that application is going to protect basically a future event. Okay. So for recap, in this session we have learned terms, edge from an IT and OT perspective, integration with the Purdue model, practical approaches, security issues in OT environments, potential data paths and applications, and some sample architecture strategies that can be deployed. Mark, back to you.
Thanks so much, Jeff. We appreciate your efforts. The audience listening live can now type questions or additional questions for today's presenter in the Ask a Question box on the screen. We'll answer as many questions as we can. Within a few days, the presentation will be available for on-demand viewing along with the link to the quiz for potential PDH credit. We'll post the archive on the Control Engineering website and send an email message out with a link connecting directly to it and related resources after it's ready. And now on to the audience questions. And you can continue to submit as we go. So the first question, what is the best cloud platform for industrial systems or IIoT?
Yeah, so the best cloud platform is the one that fits the needs of your business the best. There is variability in available technology and applications in each of the cloud offerings and ecosystems. So for example, one cloud offering could have a lot more available software and applications that are meaningful to your particular type of business and operation where another doesn't. This is all part of that part of the evaluation.
Great, thanks. Regarding cybersecurity, is there a recommended way to secure each endpoint without a lot of manual work?
So each customer or site, et cetera, has their challenges and technology evolution cycle in a facility. The OT environment in facilities does not progress at the same pace as IT, where it's difficult to completely standardize these methods. I've worked in facilities that basically have 1970s technology, 80s, 90s, et cetera, with not a lot of upgrade path, and you have to be prepared for that.
How does a remote sensor network fit into the IIoT to cloud discussion?
Okay. If I understand the question, I would view this as merely the ingestion of sensor data into the cloud storage environment where the data can be used by applications. This is basically integrating from the edge so that you can basically ingest data off the network from a client perspective.
And then can you provide tips on connecting OPC to a cloud platform and on time series data structures?
Okay. Each platform has their methods, protocols, etc. The simple answer is you need an OPC client to connect to the OPC server. A cloud should have a basically software hub that directly can feed time series storage, or you can feed the data into other types of storage like MySQL, for example. This question was a bit related to Azure. Azure in particular does have a hub that ingests OPC data. So if you have an edge device, typically you would interface with that method into time series and then transfer through the hub. There are protocols that different cloud environments support. Some may only be MQTT outside of the hub, for example.
Great, thanks. Is timing or synchronization needed between devices when working on these architectures?
Okay, that depends on the application. So if I'm ingesting historical data, which I usually classify as semi-real time, I simply need to grab data from where I left off from the last run. in real time, it is no different than how a SCADA system, for example, would ingest. However, there are limitations that can exist from the software you have chosen. So some software packages are publish subscribe, some are synchronous. That is part of the software architecture effort that needs to be performed.
Great, thanks. Is it possible to have supervisory control and active real control of a real process in a remote site by means of IIoT technology?
Yes, and I provided an example in the session where, IIoT Edge could be a PLC. Also with an edge device, I talked about the wellhead controller example, where a PLC was doing say really the direct control, and the edge device was doing the optimization of that control strategy.
Great. So can you provide examples of IIoT file integrity management and edge analytics?
Okay. So edge analytics could be applications designed for the problem in machine learning, artificial intelligence, or even a physics-based model, for example. Those are what I would call analytics. Artificial intelligence, though likely trained on a physics-based model, can replace the real-time dynamic model. Data ingestion can have an application that validates the data received is within bounds, such as limits, it's good quality from the source device, for example. And there are many other filtering methods that are typically applied in that type of work to ensure data integrity. And then file management's a little bit different exercise, but it does have similar methods to use to verify the data within the file.
Thank you. Certainly, projects vary from place to place, but are there some most overlooked considerations when forming an IIoT cloud-to-edge strategy?
Yes, the software architecture of the application is probably the biggest problem I've seen. There's a bit more focus on the hardware and some of the other physical aspects that are really the commodity part of this. And the software architecture can really make or break these projects.
Let's see, another cybersecurity question. How is that treated in a multi-tenant architecture?
Yeah, so in multi-tenant, if we're talking about, let's say, public cloud ingestion, not my own private hosted cloud. Basically, the data itself is secured to that owner on the ingestion path. So that makes the data, let's say, not accessible to others by the host company. So there is a very intricate security design that really starts from the point of connection that this is what belongs to that owner.
And then the connections up to that point would be traditional implant cybersecurity architectures. Yeah.
And ultimately, the host company is responsible for the security outside of the on the ingestion path.
Great. Here's a term question. You did a great job at defining terms in the beginning. Somebody wants to know, what is a BLAN?
Short nomenclature for business LAN, local area network.
Yeah, so that
basically
would be
where your email's hosted. Yeah.
Great. What are some of the main reasons an IIoT project might fail? So, help the listeners not do these things.
Most of the time, I'll start out with IIoT projects that are stuck and can't get started. The issue is that there have been difficulties in conveying the economic value of the project, and that does need time spent. So that's just to get you moving. The other area was often that you're impacting the manufacturing environment who another group of people are operating and maintaining. Aligning those stakeholders to the business value and why you're doing it, basically doing that internal sales job, is an area that's really overlooked. Believe it or not, most of the time, there was nothing wrong with the technology or the application intended. It was the people that made it fail.
So really what we would call soft skills rather than the hard technology of, the hardware or the software. It's how the project is managed.
That's right. That's right. We've been doing this for 30 years. Why do we need something new? Those are things that you have to be prepared to combat.
Yeah. So here's a kind of a long multi-part question. Where does the edge or the cloud reside physically, and does it leverage visualization?
Yes. So an edge device, so you can provide visualization on the edge device, similar to what we would do with a PLC application, for example. So that design is important to make sure that you have all the applications intended. So technically, you could have the edge device directly where the instruments are measuring. Of course, meeting all the requirements discussed, electrical area classification, etc. Or you could have a broader ingestion of data, for example, where maybe you have a ingestion in the control room, and you're just picking up the data off a network of IoT devices with that. So there's a lot of ways to accomplish this, and let's say choice or selection variability that you can have.
Great, thank you. So just a word to the audience as we wrap up here with the questions. If you want to continue to type in any questions you might have, we'll try to get to the rest of them offline, but I think we have room for about one more question. What is your opinion on using a SCADA server as an edge server? Hardware and data buffers already exist on this device.
So, I mean, effectively, there's cloud SCADA now as well. There's really nothing wrong with that to some degree, to do your cloud ingestion. I would have to look at the application and what you're trying to do with it before I gave you a definitive answer. But in general, SCADA is a method of ingestion, and can have methods to basically buffer data as well. But it's really making sure that you have the cost-effective solution in what you're doing also. And it depends on the platform you have, the technology you have as well.
Well, thanks everyone for the great questions. We'll try to get as many of the unanswered questions offline as we can. And thanks again to our presenter, Jeff Shannon, Director, Intelligent Operations for Wood.
Thank you, Mark.
And thanks again to our sponsor, Oracle NetSuite. And now that we're about done, we want your feedback. A short survey will pop up on the screen as soon as the webcast event ends. Please take a moment to complete it. We use this information to improve future webcasts. Finally, on behalf of Control Engineering and CFE Media and Technology, thanks for attending. This concludes our webcast. Thank you and goodbye.